Here we go. We're going to hear from Scott Gould, who's at one of the Claremont McKenna colleges. He's going to talk about using Maple to teach ODE modeled physics. I must say that my first experience in using computer algebra systems was with Maple on a VAX machine, and it just opened up my eyes to what that kind of technology can do, and it's nice to have your eyes refreshed by a talk like you're going to give us. So take it away.
Okay, so yes, I'm a physicist, but I would want to say that I share a lot of values and goals that you folks have, the mathematicians. I was never good enough to be a mathematician. So I ended up in physics, and I do applied physics in a sense. My issue is, for years, I've wanted to integrate computational science, techniques into my physics courses, but I've never been able to. The other thing, of course, I want to do is I wanted to understand what my students are interested in learning and tailor my course to it. So I teach at Scripps, Pitzer, and Claremont McKenna, which are three of the least known of the Claremont colleges. The better known as Pomona and Harvey Mudd College. And in a sense, by being a member of three colleges, I'm a member of none. And so they let us do crazy things, including for about 10 years, we taught an integrated science course where we had a year of intro bio, a year of intro physics, and a year of intro chemistry, all the same time, 3 professors in the room. We were feeding off each other. Each person would sort of do what they thought was important. And I saw very early on that my goal was to figure out how could I explain why the biochemistry that virtually all the students were interested. They had no interest in basic physics. Why physics was the principles behind those things. And if they understood more physics principles, they could go deeper into any of the problems that they were looking at. So that's what I ended up doing there. Unfortunately, at the moment, Claremont McKenna is going through a divorce, so that's why I'm now down to Pitzer and Scripps. So what did I learn from my experience of teaching with biologists and chemists for a lot? And the big deal is, and it's amazing for most physicists, they still don't get it. 99% of our students are not going to be going to get a PhD in physics. So why do we teach this way? Now, I think I'm probably preaching to the choir or the people who may be looking at this video. But I've noticed, again, even in my math colleagues, they still think that they should be teaching mathematics as if most of their students were going to go get a PhD in mathematics. That's too bad. Okay. So again, as I said, I want to show students why physics is important, and I want to teach skills that are applicable and are transferable. So to that end, I also want to add this. So to that end, I have to think about what is the pedagogy of physics. And of course, the number one pedagogy of physics is conceptual understanding of the principles. And in a sense, we should be spending all our time doing that. But as you'll see, we tend not to. With that, we, of course, do the theory part, which is mathematical representation of these principles. We do the lab part, the experimentation part, hands-on exploration and measurement. And I think what's most important now, and certainly different from when I was in college, is we can now do algebraic and numeric exploration much better than we used to be able to. So essentially, these last 3 items here, and I don't know if you can show my cursor, they are now in my book all equivalent. It's not just, there's not a separation between the math and the experiment and the computation. And my goal here is to actually combine 2 of these, and that's where we're headed. So historically, this is how computational problem solving has been done in introductory physics. We work on, of course, conceptual understanding, but then we teach them all these tricks and mathematical minutia. We actually don't talk about the mathematics. We spend more time about mathematics is just this thing, this that just gets us to our answers. There is no essentially beauty in mathematics, and that's something that we can't do because we're spending all this time teaching them memorization and technique tricks. And then, of course, if we want to add any sort of computational component, that means we are adding coding, and that just adds to the complexity of the problem. It's just like climbing a very, very tall building. And the reality is, very few people can reach that top. I have been trying to introduce computational techniques for over 30 years. I have gone through every single type of classic software package: Fortran, MATLAB, Python, C, C++, Modula 2. Actually, I liked Modula 2, Ada, several others, okay? And so what I think now, and again, I also was involved in Mathematica and Maple, but again, I found them to be just more coding time. However, I want to argue now that Maple has gotten me to the point where, and this is true, I spend now in intro physics way more time on conceptual understanding and principles. I still do mathematical representation, but I don't teach them math minutia. I don't teach them tricks. I can teach them to think about, okay, why is this representation work? Where do we see it there? And the reason why I can do that now is I can overlay having Maple do a lot of the minutia that I don't want to teach. In addition, by doing that, I'm effectively doing coding simultaneously. So it overlaps. So it's not nearly as tall as it used to be. In addition, okay, so this is my claim. What Maple, certainly any computer algebraic system, and I would say even Mathematica does, is it allows us to do a top-down problem-solving approach, which is completely counter to the way we always teach coding. Okay, so here's a classic example. We have a person bicycling up the hill. You might see the bicycles behind me. I do a lot of bicycling. Okay, I can include air resistance as proportional to speed squared. Okay, so here's our picture here. All right. So there again, I draw the pictures. These are classic techniques that I want the students to be able to solve. This is how I solve the problem in physics. All right. Draw the arrows. What are the things interacting with the bicycle? How do I define the arrows of the force of those interactions? And then I start with the very first principle. It's not set up a bunch of things and then do F equals ma. It is start with F equals ma. Where what? What is the force? The net force is that of the earth plus the ground plus the air. And I gave a talk, and I found out later that when I gave this talk, people said, oh, you never showed any Maple code. So I'm trying to remind people, this is the code. So as I'm actually doing the mathematical representation, I am coding simultaneously. That is what it's gotten to. So, and the students like this approach. Okay. So again, from the top-down approach, I can say, okay, what is the force of the earth? Well, it is a 2D vector force. Okay, it has a magnitude m times g, and it has an angle of minus pi over 2. I did it in radians, it doesn't really matter. And then you can go through the next one. Oops, hang on, my bad. Clicked on the wrong thing. All right, what's the force of the ground? Well, that's made up of friction and compression. What is the force of the friction? Well, the force of the friction is the fact that I'm providing power on the bicycle such that the wheel is pushing against the ground, but the ground is pushing me up the hill. This, interestingly enough, is the physics there that actually students have difficulty. They don't have difficulty doing this type of problem. They have difficulty understanding this part, which is fine because that is the physics part. All right. I can add in what's the force of the air. Again, a 2D vector. Notice I've not put in sines or cosines or anything yet. Why? I've just simply defined it that way. And then I finally can define, well, what do I mean by a 2D vector? Well, it's a thing with a magnitude and direction, and I can break it up into its components. And that's what it does. And so the students use their textbook and they see vectors written out this way. So now we're basically down to what is our force equation? It is now down this equation, and they didn't have to spend, and I swear, I remember spending hours going through algebra to get to this step. And then finally saying, well, let's solve the problem. Okay. It does all the manipulation for me. So that's why I can spend more time on the concepts. And then all I essentially need to do is teach them solve. They can remember solve. And then they can actually remember how to pull it out and simplify. One of the nice things is if you do this, you actually get a value for which it is comparable to the resistance as a constant. And in fact, if you use this value and ask the question, what is the steepest gradient Gould can ride up the hill for which he doesn't fall over, and you put the numbers in and it works out to be about 14 degrees, which is just about right. I can do 12. 14 is just about where I'm at, too low and about to fall over. Okay. So do I get student buy-in? The answer is yes. Why? Because it's a low barrier to generate content. I use the palettes over here to write pretty much all the commands. If I need integral, which Mathematica has many of these same features as well, but the palettes make life a lot easier. We're spending less time on teaching them how to memorize code expressions. I don't have to teach them int, what's the expression. Although I swear, some students, they actually think that doing it this way, it's not real computational, that they have to, they still have to do it by the coding technique. If it's not in Courier font, it's not true computational physics. Okay. The Maple math is written math. We get symbolic solutions. It's not a solution of just one example. And so we can say, well, what would happen if Gould lost some weight? Would things get better? Things like that. It is a minimal amount of coding that I have to actually teach them. Of course, they get immediate feedback. They complain, "Oh, Maple is not working properly." Well, maybe it's because you're putting in garbage. Okay. And it's telling you right now that first step you're doing is wrong. Let's think about the physics of that first step. Oh, early on, we do a lot of that. And then later they're totally bought into it. Okay. It is not a black box sim. It is technically, but it's nothing like our some of our simulations that we use where the students are moving things around and some magically a number appears. They could still do the same mathematics by hand if they wanted to. It's just making life easier for them. And of course, what it does do is allows me, I've been doing it for decades now. I can do linked ODEs in introductory physics, which is something that normally you can't do, even though that is how we do physics. Here's another example. This is sort of a what if example. This is a swinging Atwood. This red ball goes up and down. This blue ball can rotate around, also go up and down. And what we're interested in is the motion of the blue ball as the red ball goes up and down. Okay. And so we can write out the ODEs just like they see them in the textbook, just like they find them. They don't have to, it's readable right from the beginning and the initial conditions. We can even set up parameters which are not set by constants. We can therefore solve it, and we can essentially have floating parameters like what is the mass of the red ball relative to the blue. I can't solve this algebraically or symbolically, but I can solve this numerically, but I can solve it such that I can control what the value is for m every time. And what's that initial angle which we release the ball, the blue ball. And then eventually we can make a plot of the trajectory. So again, if you didn't follow that, again, we're going to plot the trajectory of the blue ball. The parameters are going to be varied on demand. And this is what students like. It allows them to do what if type questions. Okay. And so let's see if this works. You can see me, I can actually slide the parameter. There is the changing the relative mass of the red ball to the blue ball. I can change the initial angle, and we can change therefore the plot of the trajectory of the blue ball is. Okay. And it doesn't take that much. It's just I didn't show it. But basically, I showed you everything to do what you see on the right, and the left is just another set of equations. Okay. So how do I do maple immersion? Well, basically, I start from maple from day one.
Scott,
Yes.
the red ball is driven, right?
So the red ball just falls.
It's just free falling.
It's just free falling. It just goes up and down, and that's it. And then the blue ball, and in fact, in this configuration, with the red ball 5 times the mass of the blue ball and the initial angle of the blue ball at this angle, nearly pi over 2. This is going to be the trajectory of the blue ball as a function of time.
Okay, so this is a frictionless system, right?
Mm-hmm. Yeah.
And the red ball is only subjected to gravity, but it's also being pulled by the motion of the blue ball. Is that right?
Correct.
Okay.
With the blue ball moving, what happens is it increases the tension on the rope, and therefore that will cause the red ball to go up and
Gotcha.
down.
Okay. All right.
So, okay. All right. Let me see if I can get it. Okay. So again, how do I do this? By the way, thanks for asking a question. It's a fun little demonstration. It's fairly the Lagrangian stuff is I could have gone through, but again, you see the idea. I would approach it from a top-down approach, and then all I did was I wanted to show the numerical aspects. But I start from Maple from day one. I walk into class, I walk through, I have them, do by hand. They get started. I have some examples, but basically they are quote coding because they are both solving the problem and using Maple to get there. I present all calculation, complex derivation, Maple. Why? Because it's relatively readable. I assign problems that, of course, they cannot be solved by hand. I allow them to solve problems if they want by hand. I, of course, emphasize creating on graphics and what-if applications, visualization, because that's what we do in physics. All submissions are on Maple worksheets. That's usually not a problem. Even if a student says, I want to do this by hand, they take a picture, they import it into the document. That's not a problem at all. And then, of course, I rely on a series of videos that I have started creating myself, which teach physics Maple to them. And this was something that was always missing. So what it is, it's called the Learning Maple Maximum Productivity Minimum Coding Technique. You can find it here. That's my website. Yes, my daughter bought me a web domain, Gould.prof. So if you go there, you will see it. I also have a YouTube channel. They are terrible. I am stilted. I am not dynamic at all. This is, but they get through everything in 12 minutes. Okay. Where are we? I are the things that I've gone through. Much of this, I already have videos. Other stuff is in the form of documents that you could pull up. I'm basically gone through all the mathematics that students would need for upper division physics or engineering. Okay. So again, why do I do this? Because it allows me to go back and teach physics principles. We emphasize, spend time more of, oh yeah, why am I going up the hill? It's because the ground is pushing me up. It's not that Scott is pushing me up. The ground is, that is the external force. And it's through mathematics that they're used to. It's not as black box. It uses the top-down approach, which is completely counter to how almost all coding courses are. Just think about when you do with MATLAB, you have to sign all the numbers first, and then eventually you get to the equation. And in this approach, essentially, I start with the equation first. It reduces my math minutia and teaching tricks. I learned from Brian, who I'd like to thank for inviting him here, is that I need to spend more time, concentrating on things that actually Mike Olenek pulled up, looking, where are the eigenvectors? Where are what's going to be the eigenvalues, things like that. Of course, as I said, intermediate interface, near immediate feedback. Solutions are symbolic, which is very important, and beyond the spherical cow, like that problem right there. And of course, if the students don't stay in my physics, if they don't stay in physics, they can still use it. And they tell me they use it in other courses. Now, some courses, of course, won't let them use this, but that's okay. They can check their work. And because it goes through multiple steps, it's much more useful than Wolfram Alpha. If it's just, I have to do an ergo, then Wolfram Alpha is great. Okay. And it's not that expensive. It's cheaper than a textbook. So anyway, my suggestion is, based on my experience of 30 years, is if it's too late now, or maybe it's not too late, go sit in a STEM course, see how your mathematics is being used by people who need your course, and question everything you teach. Okay. And if you want to see more, you can go to this website, and that's where some of my stuff is. Okay. Thank you very much.
Well, thank you very much, Scott. I can feel your energy with your students. Any questions or comments from our audience? No? Yes?
I would add just a comment. Thank you very much, Scott. We have a site license for Maple on our campus, which allows any instructor to download a copy. And Maple is installed on a number of public machines. And there's also a virtual lab, so the students can run Maple on their own personal computers using the lab, so that they don't have to buy a copy of the software.
Yeah,
So that's something people might want to look into.
Yeah, no, and I totally agree. I mean, our colleges actually have site licenses for several of these packages: Mathematica, Maple, MATLAB, and then a lot of these SISTAS, and a lot of statistics packages. I am told that actually MapleSoft, and maybe it's because they're Canadian, they're actually the easiest to work with in terms of so that actually helps a lot. But yeah. But again, for those who don't have it, the cost is it's not free. I find that professors say, well, I'm going to use Python. Python is a fine language, but ask yourself, what is the activation barrier that you have to overcome? How much coding do you have to do such that the students can actually write all the code themselves? And I assure you, if you can do it faster than I can, that's great. But I have tried all sorts of other things. I teach programming in MATLAB, and I find MATLAB is terrible language, to the point where no computer science department will accept it as a standard intro programming course. But it's very popular because we have a lot of packages. But here's a way I can get them to do physics early on, the mathematical representation and the coding simultaneously.
Is the first course that they at your college, you're teaching a physics course, right?
Yeah.
Is that the first course that they see computer algebra systems, in particular Maple, at your college?
If they go through me, yes. Some of the other professors, they're not there yet. They're slowly getting there. They're seeing the advantages. I have a colleague who in the third semester, if a student takes, say, modern physics, relativity and basic intro quantum mechanics, they see Python, they see Mathematica, which I'm happy with, because it has a lot of the advantages that I mentioned here. I just find Maple is more readable.
So you're telling me the math department isn't using it?
I concede the math, and again, for us, it's the math departments. They're all over the place.
Yeah.
And there's no, we have tried in the past to come up with some sort of agreement, but it never works, because their people change and a new person comes in and says, I'm not going to use this. And in a sense, I don't care. What students can get out of it is the idea of, you should be able to solve these things, and there should be a few basic principles of the coding, and so that you can spend more time on what's the mathematical representation.
Okay, any other
Yes,
comments?
sure. I have a question. During the physics department, is that correct?
Yes.
I'm a physicist. Yes.
Yeah. I teach differential equations, and always the issue pops up is like how to balance the course. Is that you can do a lot of theory, you can do a lot of modeling, you can do a lot of how to solve various equations by hand. You can do a lot of stuff on computers. What do you like, just from your selfish physics perspective? What do you think would be the a good balance?
Well, you're talking to a person that also has to teach ODEs. So I teach a course called Computational Physics and Engineering, where basically I cover all the mathematics the students need, which is through ODEs, linear algebra, orthogonal functions, etc., transformations. I'm very, very heavy on modeling And a lot of the beautiful things that you see, say in linear algebra, I'm not going to go over in terms of the theory. A lot of my issues are, I'm interested in, they understand what matrices are, vectors are, and particularly eigenvectors and eigenvalues and where they come into it. And of course, then how do we link them at some point? At some point, we finish the ODEs, we finish the linear algebra, and then we can combine the two is the way you folks do it. But I'm definitely almost, I find there's way too much theory done in math, but that's me.
Okay.
So
Thank you very much.
so the nice thing is this is a place which I've never heard of, and I appreciate, Brian, is that you're doing lots of examples, and you've got, in a sense, I bet there's more exciting people doing math here than pretty much any other math environment. I certainly got more out of this conference for my $45 than I got over the zillions of dollars I spent for the stupid joint math meeting, which is fine. I'm not an expert here. So yeah,
Well,
I like the fact there's so many great examples here.
So the theory, the real question is, do you do the theory first? And traditionally, that's what happened. You would prove there exist solutions and they're unique and all this kind of stuff. And I think in this day and age, the students are just not going to tolerate that. I mean, you know, students have a point of view, and there are clients, if you will. And some stuffy professors don't look at it that way, you know, but so they can get to the theory, but let's show them why we would even study the subject in the first place. And I think I'm seeing the nods, and, you know, we're in the choir here. And so,
Yes.
but at the same time, I think we see the joy in the students. And if a language and a use of a computer algebra system is helpful, and I'm with you, I believe it is, then it expands what real things we can show them. And I guess the other question is, you don't formally track them, but they can use this beyond, and I suspect a good number of them really do use it beyond, not just to check their answers, but to actually do, you know, their undergraduate research or whatever they're doing.
Yeah, no, I do, because a lot of them, what they'll do is, the way our system works is they get a code for just that year, academic year. And when they move to the next academic year, the code does not work. So I'll get emails like, how do I get Maple to work now? I was like, okay, well, you're going to download the next version, and here's the code number for the next version. So I certainly hear that quite a
That's
bit.
good.
I also hear it from graduate students who would like to get a copy because they use it in graduate school. So.
Yeah. But listen, I want to thank you very much again for joining us. And
no, thank you.
All right, take care
Right.
now. Bye-bye.
Nice meeting you.
Take care.
Bye-bye.
Good to see you, Scott.
Nice to see you. Thank you.